Every time you switch on a light, charge your phone, or power a factory, electricity begins a journey that often started hundreds of kilometers away. In many parts of the world, that journey doesn't begin with coal, oil, or natural gas. Instead, it begins with something much simpler: water. Hidden behind massive concrete walls, billions of tons of water quietly wait at a higher elevation, storing enormous amounts of energy. At first glance, a hydroelectric dam appears to be nothing more than a barrier holding back a river. But behind that wall lies one of the most efficient methods humans have ever developed for generating electricity. The remarkable part is that the water itself is never consumed. It simply flows through the system, transfers its energy, and continues its journey downstream exactly as nature intended. The story begins long before electricity is produced. Rain falls across mountains, forests, and valleys, feeding streams that eventually join together to form rivers. Instead of allowing this water to flow directly toward the sea, engineers build a dam across the river, creating a large reservoir behind it. This artificial lake serves as much more than a place to store water. It acts as an enormous energy storage system. Every drop of water held high above the river below contains gravitational potential energy simply because of its elevation. The higher the water is stored, the more energy it possesses. Many people imagine that the water inside the reservoir is constantly trying to escape, and in a way, that is exactly what is happening. Gravity continuously pulls the water downward, but the dam prevents it from flowing freely. As more rain and river water enter the reservoir, an enormous amount of potential energy accumulates behind the concrete structure. This stored energy can remain available for days, weeks, or even months until electricity is needed. When power generation begins, operators open specially designed intake gates built into the dam. Water immediately begins flowing toward these openings because gravity is pulling it to the much lower river on the opposite side of the dam. As the water enters the intake, protective screens prevent logs, branches, rocks, and other large debris from entering the power station where they could damage the equipment. From the intake, the water enters one of the most important parts of the entire system, a massive pipe known as the penstock. Although it looks like a giant steel tunnel, the penstock has a critical purpose. It safely carries enormous volumes of water from the reservoir down toward the turbines while maintaining controlled flow conditions. As the water travels downward through the penstock, its speed increases dramatically. Gravity continuously converts the stored potential energy of the elevated water into kinetic energy, meaning the water is now moving with tremendous force. By the time the water reaches the bottom of the penstock, it carries an enormous amount of energy. Instead of allowing that energy to disappear downstream, engineers place a turbine directly in its path. The turbine resembles a giant wheel fitted with carefully shaped blades. As the high-speed water strikes these blades, it pushes against them, forcing the entire turbine to rotate. The shape of each blade has been carefully designed to capture as much energy from the moving water as possible. Rather than stopping the water completely, the blades guide it smoothly through the turbine while extracting a large portion of its energy. Different hydroelectric plants use different turbine designs, depending on the height of the dam and the amount of water flowing through the system. Some turbines are built for extremely high waterfalls, while others are optimized for lower heights but much larger water volumes. As the turbine begins spinning, something remarkable happens. Water itself is not electricity. Instead, the moving water simply provides mechanical energy by rotating the turbine shaft. That shaft is directly connected to an electrical generator positioned inside the powerhouse. Inside the generator, powerful magnets rotate around tightly wound coils of copper wire, or in some designs, the coils rotate around stationary magnets. This movement creates one of the most important discoveries in the history of science: electromagnetic induction. Whenever a magnetic field moves relative to a conductor, an electric current is produced. The generator converts the mechanical rotation supplied by the turbine into electrical energy without any combustion, flames, or explosions. The faster and more consistently the turbine rotates, the more electricity the generator can produce. However, maintaining a stable rotational speed is essential because electrical grids require electricity at very specific frequencies. Control systems continuously adjust the flow of water entering the turbine to maintain the correct operating speed, even as electricity demand changes throughout the day. After passing through the turbine, the water has already transferred much of its energy to the rotating machinery. It exits through a large channel called the draft tube before rejoining the river downstream. Although the water has lost energy, it has not disappeared. It continues flowing naturally through the river, eventually becoming part of lakes, other rivers, or the ocean, before beginning the water cycle once again through evaporation and rainfall. The electricity leaving the generator is not immediately ready for long-distance transmission. Inside the powerhouse, transformers increase the voltage to extremely high levels. Raising the voltage allows electricity to travel hundreds of kilometers, with much lower energy losses. Thick transmission lines then carry this electricity across cities, mountains, forests, and entire countries until it reaches substations closer to homes and businesses. There, the voltage is gradually reduced again before finally entering local distribution networks that deliver usable electricity to consumers. One of the greatest advantages of hydroelectric power is its ability to respond quickly to changing electricity demand. Early in the morning, millions of people begin preparing for work, turning on lights, kettles, appliances, and heating systems almost simultaneously. Electricity demand rises rapidly. Hydroelectric plants can respond within minutes simply by opening the intake gates further, allowing more water to reach the turbines. As demand decreases later in the day, the gates can be partially closed again, reducing water flow while maintaining efficient operation. Unlike many other forms of power generation, hydroelectric stations do not need to burn fuel to produce electricity. There are no truckloads of coal arriving every day, and no natural gas pipelines feeding large combustion systems. The energy comes directly from water that has already been lifted by the natural water cycle. The sun evaporates water from oceans and lakes. Clouds transport that moisture across the atmosphere. Rain falls over higher elevations, and rivers carry the water downhill. Hydroelectric dams simply capture part of this naturally occurring energy before the water continues its journey. Engineers carefully design every component of the dam to handle enormous forces safely. The reservoir behind a large dam may contain billions of cubic meters of water, creating tremendous pressure against the concrete wall. The deeper the water, the greater the pressure exerted on the structure. For this reason, hydroelectric dams are among the largest and strongest civil engineering projects ever built. Their foundations extend deep into solid rock to support the immense loads they carry. The spillway is another critical safety feature. During periods of heavy rainfall or rapid snowmelt, more water may enter the reservoir than the turbines can safely process. Rather than allowing the water level to continue rising indefinitely, excess water is diverted over or around the dam through spillways. These structures safely return surplus water to the river below, while protecting the dam from overtopping. Modern hydroelectric facilities rely on sophisticated monitoring systems that continuously measure water levels, turbine performance, structural movement, vibration, temperature, and electrical output. Thousands of sensors provide real-time information that allows operators to detect even minor changes before they become serious problems. Many plants can now adjust operations automatically using advanced computer control systems. Hydroelectric power stations vary enormously in size. Some small installations generate enough electricity for a remote village using a modest river, while the world's largest dams supply power to millions of homes across multiple regions. Despite these differences in scale, every hydroelectric plant follows exactly the same sequence of energy conversion. Water stored at a higher elevation contains potential energy. Gravity converts that potential energy into moving water. The moving water spins a turbine. The turbine rotates a generator. The generator produces electricity. Finally, the water returns to the river to continue its natural journey. One common misconception is that hydroelectric dams consume water during electricity production. In reality, the water is simply borrowed for a short period while passing through the turbines. Unlike fossil fuels, which are permanently consumed during combustion, the same water remains part of the Earth's natural water cycle after leaving the power station. Another important benefit is efficiency. Hydroelectric turbines convert a remarkably high percentage of the water's available energy into useful mechanical power compared with many other forms of electricity generation. Combined with their long operating lives, relatively low operating costs, and ability to respond quickly to changing electricity demand, Hydroelectric plants continue to play a major role in power systems around the world. However, building a hydroelectric dam also presents significant engineering and environmental challenges. Large reservoirs may flood valleys, alter river ecosystems, affect fish migration, and require communities to relocate before construction begins. Engineers now work alongside environmental scientists to reduce these impacts through fish passages, environmental flow management, sediment control, and improved reservoir planning. Modern hydroelectric projects increasingly seek a balance between renewable energy production and ecosystem protection. Researchers continue improving turbine efficiency, developing fish-friendly turbine designs, enhancing dam safety monitoring, and integrating hydroelectric plants with solar and wind energy systems. Some facilities also operate as pumped storage plants, storing excess renewable electricity by pumping water uphill during periods of low demand, and generating electricity again when demand increases. In this way, water becomes not only a source of renewable energy, but also a giant battery capable of storing electricity for later use. Imagine standing beside an enormous reservoir early in the morning. The water appears perfectly calm, almost motionless. Yet hidden within that still surface is enough stored energy to power an entire city. The intake gates open, and gravity immediately takes over. Water rushes down massive steel penstocks toward giant turbines deep inside the powerhouse. The turbines begin spinning, generators come alive, transformers raise the voltage, and within seconds, electricity begins traveling through transmission lines toward homes, hospitals, schools, factories, and businesses hundreds of kilometers away. Moments later, the same water quietly leaves the turbines and returns to the river, ready to continue its endless journey through nature once again. The dam itself never creates energy. Gravity does not create energy either. Instead, the entire system simply captures energy that already exists in elevated water and converts it into a form that powers modern civilization. It is one of humanity's greatest examples of using the forces of nature rather than fighting against them. That is how hydroelectric dams generate electricity,